Okay, good morning. Let's get started. So we've been talking about feedback, and I gave you a number of explanations about what feedback is and why we need it and so on. Please, if you quiet down a little bit, just even in the back rows. So I'm going to give you a few other explanations or examples of feedback in the hopes that then everybody will understand that feedback is something totally natural, and it also happens in operation amplifier, but in different situations as well. So this is a situation that may have happened on the weekend. A car in the front you're following, and you want to follow it at a constant distance. So you want that the speed of your car and the car in front of you, that they're just the same, right? So both of these cars, they're going at, let's say, this is a speed VA, and this speed VB, right? So, well, the first thing, of course, you have to observe these speeds, and then you have to take their difference. So here we have speed VB, and here we have the speed of your car, that's speed VA, and you take the difference between the two, and that's the difference of the speeds, right? So now, if, for example, VB, the speed of the car in front of you, is a little bit higher than the speed of your own car, the speed VA, then this quantity here is positive. What are you going to do? Yeah, you want to speed up a little bit, so you press a little bit the accelerator. So in other words, you put an amplifier here. Depending on how you want to call this thing, you can call it a motor, or you can call it an amplifier. But it's really just an amplifier, right? It amplifies the little signal that you apply to the gas pedal, and it puts out a really large torque, at least if you have a strong motor, right? Okay. And then the dynamics of the vehicle, they turn this torque back into a velocity, and that's the feedback loop. Okay? Totally natural. You do this all the time. You never ask any question about is it negative feedback or whatever, right? It happens to be negative feedback, you see here. Negative feedback. Feedback, you apply this all the time. For example, when you're driving a car, and I'm sure there are lots of other examples. Notice also this speed here, the difference between the two speeds. What is it? 0. It should be 0, right? That's exactly that voltage Vx, how we call it in operation amplifiers, right? That voltage should be very small. Well, here it's obvious, right? We want the two speeds to be identical. And there is even one other thing. Suppose that the vehicle in front of you speeds up very, very rapidly. What's going to happen? You want to speed up your car very rapidly also, right? How are you going to do that? You're going to need a big motor, right? You need a big amplifier with gain infinity, right? Ideally infinity, right? Then you can keep the two speeds the same, even if the car in front of you accelerates very rapidly. Now, maybe the car in front of you doesn't have an amplifier motor with infinite gain either, and so then you don't need quite infinite gain to keep up. But it's exactly the same situation. In fact, we can see the operational amplifier in here, right? This whole thing here acts just like an operational amplifier. So when you're driving a car, you're just sort of simulating an operational amplifier in your head. Okay? So, yes?
What does that mean?
What does... This symbol here, yes, it's usually, it's very commonly used for summation. So I want to take this one positive, this one negative. So what this block does, it takes the difference of VB minus VA. Good question. Yeah, so you will probably see this symbol in many other courses throughout your career here at Berkeley and later as engineers. So these signal diagrams, feedback also, they're very, very useful, very common. Okay, so here one other way to look at feedback, and this one's a little bit trickier and so on. So as I said, I give you a lot of explanations of feedback. Hopefully one or the other, one or maybe several, one of them, they click, right? All right, so here we have a feedback circuit that actually is an electronic feedback circuit. It uses an operation amplifier. Let's suppose that we start here, that we initially, let's say, the voltage Vi is 0, then the voltage V out is also 0, and then the voltage Vf is 0. But now let's suppose that we put in 1 millivolt, okay? Okay, so we now set Vi equal to 1 millivolt, while Vf is still 0, and consequently Vi minus Vf is 1 millivolt. Okay? And then what is V out going to be? Well, if the gain, I set here the gain to just 1000, because if I set the gain infinite, it wouldn't fit on my page, right? So then V out is going to be, well, if Vi minus Vf is 1 millivolt and the gain of this thing is 1000, then V out is going to be 1 volt, right? 1 volt. So then, of course, immediately thereafter, Vf now is going to be half a volt, right? Okay. So now Vi is still 1 millivolt, but Vf is now 0.5 volts, so Vf minus Vi drops to minus 0.49 volts. Okay? And then the output voltage now is going to be well, it's simply that going to be this is going to be amplified. So minus. Wait a second, did I do something wrong? Oh, yeah. So then minus. What did I do here? There's something strange. I actually even wrote this on a piece of paper. I didn't get that. So Vi is a millivolt. Vf now is 0.5 volts. Then Vi minus Vf is minus 499 millivolts, right? And now we are amplifying this, and that gets minus a very big voltage. And then I'm not sure, did I do something wrong? Well, what should happen is now
is it that the discrete time steps is introducing?
No. That's not. What's going to happen is that this thing approaches. Well.
It should exponentially decay.
Yes. It will ultimately, so it will rattle up and down and so on. Ultimately, the output will approach 2 millivolts, right? And then Vf is going to be 1 millivolt, okay? And the difference Vf minus Vi is going to be 0 millivolts, right? So I guess going through all these steps is kind of but ultimately the output sort of instantaneously varies wildly, and ultimately the output converges towards that right voltage 2 millivolts. I guess maybe I'll run a simulation at some point and I'll show it to you. But so there is one more thing that we can see here, and that is this is Vi minus Vf actually is not exactly 0 in this case. Why not? Yeah, if the output voltage is the correct value, right? The gain of this thing is actually 2. If the output voltage is 2 millivolts, then the difference here is going to be the output voltage divided by the open loop gain of the amplifier, which is 1,000. So we actually get here about 2 microvolts, right? And so we have a small error. So then obviously Vf isn't going to be exactly 2 millivolts, and Vout also is going to be a tad bit off. So this is the error. The error that we are going to make. The output is going to be off by 2 microvolts. How can we make this error smaller? Yeah, exactly. We can increase the gain, right? If we increase this gain here, then the error will go down. Okay? Yes?
So you start with Vf is equal to 0, and then why do you jump to Vf is equal to 25?
Because if Vi is initially 0, then and then the jump happened here, right? Here we go from 0 volts to 1 millivolt. Okay? And so the output then jumps to 1 volt, and Vf is simply, it's a voltage divider, 2 identical resistors, has a gain of 1/2, so then Vf has to go to 0.5 volts. Okay?
So Vi starts from 0 and then jumps to 1.
Yes, so that's right. So we start out at 0. Yeah. This is just an example, right? And even that, I threw this out of the course because it always gets kind of confusing because it is transients. But that's what's happening, right? The output sort of varies wildly, and then it converges in such a way that this error is going to be very small, or ideally actually going to be 0. Okay? All right, so that's what's happening with negative feedback. Now, we also could have positive feedback, and I actually told you that whenever we look at an op-amp circuit, the first thing you have to do is you have to look at whether the feedback is negative or positive. And here it's positive. Why? Well, what we are feeding back, there's only one person awake. What we are feeding back goes back into the positive terminal of the operation amplifier. So I told you before that most of the time we are using negative feedback. For example, in the example with these cars, positive feedback wouldn't be good. What would happen? Yeah, you would smash into the car in front of you, right? So don't use positive feedback there. But positive feedback does have its uses. It's less of, whatever, right? I mean, the positive feedback is used in many cases. But in op-amp circuits, most of the time we're using negative feedback, okay? Most of the time when we analyze in detail feedback circuits, we actually want negative feedback. But again, occasionally it's positive feedback, so be careful and check, okay? Okay, so but now let's look at what happens with positive feedback. Let's imagine that we again start out where the input voltage is 0, the output voltage is 0, then the voltage Vf here is also 0, and the amplifier is amplifying 0 minus 0 and produces 0. So it is sort of a quasi-stable point, right? So we are just everything 0. That's where we are starting. Now, let's assume that we again bring up this input from 0 to 1 millivolt. Okay? So what's going to happen? Vf is still, initially at least, Vf is still 0. What's going to happen to the output of the op-amp? It should go to what voltage? Yeah, minus infinity actually it should go to, right? Because the input is, here we have 0 volts, minus 1 millivolt. The input is minus 1 millivolt, that difference. The amplifier amplifies this with a very, very large gain and gets minus infinity, right? Now, in practice, of course, that's not going to happen. Anybody has an idea what is going to limit the output of the op-amp in that case? Yeah, it's some voltage, right? And the voltage that matters here is, I'm just going to write it like this. I'm not going to actually draw sources. But we're going to have supply voltages that we apply to this operation amplifier. Again, very often we don't bother showing them in our circuit diagrams, but of course they have to be there, and they're going to be finite. They're not going to be infinite, right? And consequently, the output of the op-amp actually goes from 0 to minus the supply voltage. It would like to go even more negative, but it can't, right? Because that's all there is. It goes to minus the supply voltage. If we make Vi more positive, it just keeps stuck there. It can't go more negative, right? So then, let's assume that now we reduce Vi. For example, let's reduce Vi to 0. What happens? Well, the output of the operation amplifier is still VSS. What? So VSS, right, can be a negative number. And the output is still VSS. And then we divide that maybe by 2 or so, whatever the divider ratio is of the two resistors. Then the voltage here, anyways, is still positive, right? Voltage here is still larger than 0 at the positive terminal of the op-amp. So we have a voltage that is larger than 0. Again, perhaps it's VSS over 2. And we subtract from it now the new input voltage that is 0 volts. What do we get? Still a positive voltage, right? We amplify this by a very large factor, and the operation amplifier is going to, sometimes the term is used, railed. It's going to rail at the negative supply, and it's going to be stuck there, right? Until what point is it going to be stuck at minus or at VSS, right? The output. What do we have to do in order to get the output to change? Right? Somehow we started out at 0, right? And then we just stuck in a very small voltage, a millivolt. I could have used a microvolt also, a nanovolt. And then we go to minus VSS. What happens if we now travel in this direction? Well, if Vi becomes negative, then at some point Vi is going to be sufficiently negative that whatever we have here, Vf minus that negative number actually gives us 0, right? And then ultimately becomes a negative number, or actually positive number. Right? Okay, so as we travel in this direction, there is a critical point here when Vi is equal to VSS times, well, there is a voltage divider. When Vi is equal to Vf, and Vf is going to be VSS times R2 over R1 plus R2, right? When the output voltage is at Vs, then Vf has the value VSS times whatever that voltage divider makes it to be. So at some point, at this voltage here, they're going to be equal. And then if I make Vi just a little bit more negative,
No, would you need to? Once they're equal, doesn't the output drop to zero and then you get that?
okay, maybe then the output drops to 0. Yeah. Okay, so that there is just one, one point when the output drops to 0, and then we would be at this point. And if you then make the Vi, the input, just a little bit more negative, then we go all the way the other direction.
Wouldn't the output dropping to zero make the difference across the inputs? And so it go all the way without?
Yeah, that's right. That's right. So then it goes in this direction again. Then it amplifies, has now a positive difference at its input. It amplifies that, and it's again going to be railed. It's going to be limited by the positive supply. Okay? So the op-amp, the output voltage takes the path where it first goes up like this, and then it goes back like this. Okay? And now you can go and go through the exact same thinking. If now you increase the input voltage again, the output's not going to flip until the input voltage reaches this value VDD times R2 over R1 plus R2. Okay? And it goes on this path. Okay? So you will have to go through this again to solve or to complete the pre-lab for lab 3. All right. So now let's step back and let's look at what this thing tells us. Well, apparently we can get to one output, and then we have to. We cannot just simply go back where we came from, right? It doesn't go through 0, so we have to actually remove more of the input to get back. So such a circuit, it's called a Schmitt trigger, and I guess I wrote this here at the bottom. This is called Schmitt trigger, and it's useful as a decision circuit. Imagine that, for example, you want to build a thermostat. You want to set the temperature in your room exactly to 20 degrees Celsius. Now, suppose that the temperature is... So the way the thermostat works is that if the temperature is below 20 Celsius, the heater turns on. If the temperature is above 20 degrees, the heater turns off, right? Most thermostats actually work like this. Okay? They simply turn the heater on and off. Well, suppose that the temperature in your room now is exactly 20 degrees. What's the heater going to do? Yeah, it sometimes turns on, then it turns off, on, off, and so on. Right? It would be the same thing if you had a controller that turned on the lights in a room when the illumination drops below a certain value. Just when it is at that threshold, the lights turn on, turn off, turn on. It's going to drive you crazy, right? So then we actually want a circuit like this. This characteristic here, it's called hysteresis. So we turn it on, and then it stays on for a while until we really, really want to turn it off again. So for example, that the thermostat, we may give it half a degree, right? The temperature has to not only drop back to 20 degrees, it has to drop back down to 19.5 degrees. Only when it is when it is 19.5 degrees, then we turn the heater on again, and we'll turn it off only when the temperature is 20.5 degrees. Right? So very useful thing, and actually in the lab that you're going to do not this week, but next week, which you have to design all by yourselves, you're going to use one of these circuits because there, indeed, you run into a situation where it would be very inconvenient if this thing would turn on and off very wildly. Okay, one more thing. When we are analyzing operational amplifier circuits, what are we going to do? First thing. Yes, exactly. First we check what type of feedback we have. So again, most of the time it's going to be negative feedback. Here is the output. We feed back to the input. This is negative feedback. So that's the first thing we have to do. The second important thing, if we have negative feedback and it's high gain, what can we use? What is the property that we can make use of when we analyze now such an op-amp circuit? Yeah, exactly. These two voltages here, this voltage difference is 0 volts, okay? Because it's negative feedback and it's high gain, all right? So in that case, only in that case, but that's a very important case, then that voltage is going to be 0. And the reason it's 0 is that the operation amplifier makes it 0, okay? Much like when we are driving that car, we make the difference of velocities 0. Okay? So now you can analyze this circuit again in any one of a gazillion different ways. One of them is node voltage analysis. And then, when we use node voltage analysis, we have to figure out which equations to write. So let's go through that. There is a slight modification to the general rule in this case. So again, we have to introduce a common node. We always have to do that if you use node voltage analysis. And then what's the next step? What's the next step in node voltage analysis? Yeah, we have to label all the nodes, all the node voltages that we don't know. Okay? Then we have to write nodal equations. Now we have 4 unknowns, we need 4 equations. Well, if we have op-amps, then the first equation that we're going to have is always going to be V plus is equal to V minus. Or the difference of these two voltages is 0. Same thing. Okay? Node voltage analysis, we always have this equation first. And then we're going to write equations for V plus, V minus, and V1 in this case. Okay? Yes? Why they have to be equal? Well, that's what feedback does for us, right? Remember that car example? We use feedback for what purpose? Well, we use it so that the speed or the velocity of both cars is identical. Well, once they are identical, the difference is 0, or they're the same, right? Okay? So feedback does this for us. And instead of every single time calculating this and proving to ourselves again that, well, feedback makes the difference 0, we say at some point, well, now we know it. We're not going to demonstrate it for every single circuit over and over and over again. We just know it. And we stick it into a circuit. We use that property now. But of course, you always can say, well, you know, I'm not sure. And then you can go back and you can look at the nodes and you can calculate it again. And you'll find, well, that difference is 0. Okay? And of course, I recommend that you do that until you're really convinced that that difference indeed is 0. Yes?
So the reason we can say this is negative feedback, in spite of the fact that the output also is the positive input, is just because there's a link to the negative, and that forces it to be steady state.
Right. The reason we can say that is some of the output is taken and it's fed back to the minus terminal of the op-amp. This here, that's not a feedback loop. That's actually a very good question. Why is that not the feedback loop? Well, the reason it's not the feedback loop is that this voltage here is ground. Any current, for example, if let's say we put the resistor here, that's a very good question. If we put the resistor here, of course, current flows through this resistor. But will any of this current flow into this node here and therefore provide feedback? Yeah?
There's no current flowing back. This one goes to the ground.
Exactly. The current will disappear into ground. Why? Well, because ground is a zero impedance node, right? It's tied solid through a 0 ohm resistor to the negative terminal to the supply. The current isn't crazy. Electrons are just like students. They don't put up a lot of work if they don't have to. Right? If there is a path of 0 resistance, they're going to take it. So this current all is going to disappear here. None of it is going to make it back up here. Okay? And because of that, this thing that maybe looks to somebody who doesn't know circuits, looks almost like another feedback loop, actually isn't. There is no feedback there. That was a very good question. Thank you for asking it. Yeah.
Did you just write in that branch's reference?
Yeah, the ground wasn't there. It didn't put it.
Yes, so what you're saying is if I hadn't put the ground node there, if I had put the ground node somewhere else, I guess you're right. It's obviously possible to have circuits where there would be positive feedback. You're right. If I hadn't put the ground there, I would have had to put it somewhere else. For example, I would have put it here. And then, yes, this would have been a positive feedback circuit. You're right. You're right. So I guess I should be more careful when I draw these circuit diagrams. If I do not introduce a ground node, then maybe it's a little bit up in the air. Is it positive or negative feedback? Because which feedback loop actually matters? You raised your hand again. Do you have another question? Okay. So that was a very good point. Thank you for asking that question. That was an important thing to point out. So if we put the ground here, which is also the same as putting it here, right, because there is a wire, then clearly this circuit has negative feedback. And now, again, we can apply node voltage analysis to analyze circuits with negative feedback. And the only thing that we have to be aware of is that the equations that we write down are a little bit different. The first equation we are always going to write down is that it's sometimes called summing node constraint, that the voltage at the two inputs of the operation amplifier, those voltages are going to be equal or the difference is going to be 0. Okay? And so we have an equation. Then we're going to write the other node voltages, and I showed you the nodes for which I'm going to write the node voltage equation. Okay? So for example, we could write the node voltage equation for V1. Right? That would be I1 plus V1 over R1 plus V1 minus V out over R4. Is there another one? What about R3? Actually, yeah. Actually, I guess I can write that. Plus V1 minus V minus over R3 equal to 0. Okay? Okay? So I can write in total I have 3 node voltage equations now. One of them I didn't write. Which one didn't I write? Well, what are the unknowns in our circuit? V1, V plus, V minus, and the one that you're probably most interested in, V out, and we're not writing an equation for V out. Okay? So what we're doing when we do node voltage analysis with operation amplifiers, we are eliminating the equation for the output node, this one. We're not going to write that equation. Otherwise, we would have one too many, right? We have 4 unknowns. But we already have 4 equations without the equation for V out, right? We have 1 equation here, and then we have 3 more. Okay, for V1, V plus, V minus. right? So we're not going to write an equation for the output node. And then we have the right number of equations, we can solve them, we get all the right results, yes. That's right. There's no current flow in R3. Yes. You can drop it and you still get the right result. Okay. Okay, so the modification of node voltage analysis. Yes. Yeah, in this case, you would simply write V minus V1 over R3 equals 0. That's all you write. And then, of course, you would find that V minus is equal to V1, right? And from that, solving the equations, you then find that V plus is equal to V minus, and it's also equal to V1 or so. Right, so, of course, I could have made the example more complicated, and now my diagram gets a total disaster. But if I introduce another resistor here, then it wouldn't be so trivial. Okay, works in any case. In this is actually a good example where I rarely use node voltage analysis when I analyze simple circuits with operational amplifiers, because you really write more equations than you really need. By inspection, you can write many fewer. Right? We just automatically saw that V1 equals V minus equals V plus, so why writing that many equations for that? So I'm not telling you that you should use node voltage analysis in any particular case, but this example simply illustrates how to do it. And because I made it such a big mess. So again, I'll try to summarize because this got a little bit messy. So we are gonna, first of all, we have to introduce the ground node, which also tells in this particular case that it's negative feedback. Then we have to identify all the unknowns, V1, V minus, V plus, V out. And then the first equation we write is V minus equal V plus, and the other three equations we write are V1, V minus, V plus, the node equations, and we are not writing an equation for the output. Okay? That's the schema you're going to use. If you want to use node voltage analysis, yes.
If the circuit diagram gave you the ground up in the top left, could you decide you don't like that or move it on the bottom?
Well, no, you couldn't. Then really it would be a positive feedback circuit, yes. Yes.
And part of why you can't arbitrarily just pick some random ground node when you've got another, I'm going to say I'm going to change my reference frame and say this will be ground instead of that one. Is the reason you can't do that because part of the operational amplifier is grounded?
Well, yes, there may be other constraints in the circuit there may be other constraints in the circuit. I guess in this particular case, I suppose you could put the ground on the other place and then you would indeed get positive feedback. Well, no, we would actually, there is no connection here. We would also have to put the connection there. Otherwise, there is no feedback whatsoever, actually. So it wasn't that bad. But, all right. So I'll be careful to, in homeworks and assignments and exams, and so I'll be careful to make it clear that there is a ground and it's clear whether it's positive or negative feedback and so on. So I'm not going to try to pull your leg on that. I'm not going to try to ask questions that don't have a right answer. Okay? So, but it was a good point. Yes? Oh, okay. V plus over or 2 plus I2 equals 0.
Are we neglecting the outlet because there's no current going in the outlet?
That's right. Yes, these two currents, they're 0. Always. Otherwise, we have a bad op-amp. Okay. So now we talked about a lot of things and about cars and all sorts of stuff. Like, obviously, I would like or want that you understand feedback. So here I try to list all the kinds of things that you actually, out of all this tour, you actually need to keep. Okay, so you need to know the properties of ideal op-amp. So your question, the current into an ideal op-amp, into the input of an ideal op-amp is 0, right? You need to know that. The gain is infinite, okay? And the output voltage is simply the the difference of the input voltage multiplied by the gain. Okay? So then occasionally we actually make the gain of an operational amplifier not infinite, right? And we did a couple of examples with that. I would like that you can do that also. If ever I tell you in a circuit, hey, you know, the gain of that operational amplifier is not infinite, well, then you should still be able to analyze it. Be careful. In that case, if the gain is not infinite, this is no longer true. Right? If the gain is not infinite, we saw that in this. Oh, where do I have this? We saw that in this example. Ultimately, if the gain is not infinite, if the output voltage here should be 2 millivolts, while the input voltage is, the difference of the input voltages is the output voltage divided by the gain, that's 1,000, well, that's 2 microvolts, and that's not 0. Okay? If the gain is not infinite, the difference of the input voltage is not 0. And there is actually a homework where you analyze that also. So, and there again, the point of that homework is that you look at it and, oh, that's why it's not 0. Now I calculate it myself. It's not just that this guy told me. I saw it myself. Okay? So, the other non-ideality of op-amps that we occasionally use, especially when you have positive feedback, is that they got to have a supply. Never forget that in the lab. They're not going to work if you don't give them power. And secondly, it's like a car without gas in the tank. And then also in the output is not going to go outside the voltages set by the supply. Okay. So the next thing is this positive and negative feedback. And again, if in doubt, maybe you assume it's negative feedback because most of the time you're going to be right. But it would be better if you actually can go and look at the circuit. This one's negative feedback. Okay? So open and closed loop gain. I had a slide on that, right? There is the gain. There is the gain of the operational amplifier itself, which is V out over V plus minus V minus. And then there is the closed loop gain. That's the entire circuit V out over Vi. And they are usually not at all identical. This one in particular should be, if the op-amp is ideal, it's infinite. And the other one, of course, should not be infinite, right? So beware of these two different gains. Know them. If you are puzzled about them, go back in the notes. There is a slide on just that defines them. Okay, well then you should be able to calculate that closed loop gain, AV. If I give you a circuit with an op-amp, for example, the one that we just had here, then you should be able to calculate the gain. What is the gain of this circuit? Well, it's simply V out over, for example, I1. Well, that maybe would be RV, right? Okay, so you should be able to calculate this gain using any kind of analysis, right? Very often it's sufficient to use the summing node constraint, and it's fairly trivial to write a couple of equations and solve. If it's not so trivial, you know how to use node voltage analysis, and then you can analyze these circuits like a computer. You can analyze any one of them, no problems. It's just a little bit of work. Okay, and then the final thing, and that's really, again, why we are doing all of this, is Suppose that you're in a situation, you have a small voltage, millivolts, and you would like it to be bigger. You need a certain gain, for example, 20. You should be able to design a circuit that has a gain of 20, or minus 20, or whatever, any other number. Okay? So those are the things that, of all of what we talked about, this is the stuff that's going to be on the midterm, on the quiz, on whatever, right? This is what you should carry away. And if you have questions, we have another few minutes. And if they come, yes?
You did a good example on negative feedback, but what assumptions, I guess, do you make when you have a positive feedback system?
Yeah, unfortunately then, if you have positive feedback, the difference of these voltages no longer, of the difference of these voltages here is no longer zero, and then you have to analyze it kind of by inspection, like I did. I do not know of, I'm not aware of a formal technique on how to analyze these circuits. Also, they are kind of multi-valued. They're multi-valued circuits, right? For any particular input voltage Vi, you actually get potentially two different values or even more different values of output voltage. So you have to analyze it by actually understanding circuits. Okay? All right, I'll see you Wednesday. Again, if you have any questions about any of this, please come see us during office hours. From now on, I will assume that you know this.